All right, guys, I am here to recap or review or rehash the 6 types of graphs that we learned in class. So I'm going to go through this stuff kind of briefly, and this is exactly the notes that we wrote down while we were in class, but you can fast forward if there's a specific type of graph that you want to review, or if you have questions on it or you want to rewatch, that's fine. But the circle one, there probably aren't very many questions on that, but just remember some of the connections we made in class. If it's positive sine, it's on the positive y-axis. If it's positive cosine, it's positive x-axis. Negative cosine, negative x-axis. And that helped us kind of sketch these two down here. Again, it's positive cosine, so positive x, negative sine, negative y. Another thing that we talked about was the a value, so this number that leads the either sine or the cosine, that's the diameter of the circle. And so one of your points is always on 0, 0, as you can see. And then the other point is the diameter in the direction of either negative sine, negative cos, positive cos. So that's stuff that we wrote down here. And the circle always touches 0, 0, like I said. That was a very brief example of the circle. Just keep in mind, main point is whether the sine is positive or negative, tells you positive y-axis or negative y-axis. If the cosine is positive or negative, positive x-axis, negative cos-axis, negative x-axis. Okay, I'm going to go down to number 2, the rows. So this one was a little bit trickier. It was a little weird, but a lot of you came up with right away whether or not you were supposed to double this number right here, this n that we have in our formula, which is down here, or whether you just keep the n. And so remember, if it's an even number, that means you double that number and you get 4 petals. If it's an odd number, you keep it, and that is the number of petals you have. So that's the first thing that's a little bit tricky. The second thing we talked about is where's the first petal location. All 3 of these are cosine, and all 3 of these petals right here are on the positive x-axis. That's where you start. Okay, so for sine, again, it follows the same type of rule where if this is even, you double it to get 4 petals. If it's odd, you keep it to get 3 petals. But notice where that first petal is. It's not on the x-axis, it's in the first quadrant. And so how do you figure out that first petal location? I wrote that down here. You take 90 divided by n. So in this case, 90 divided by 2 is 45, and that's why my first petal is exactly at 45 degrees. In this case, I'm taking 90 divided by 3, and that gives me 30 degrees, and that is why my first petal is at 30 degrees. In this case, 90 divided by, there are 8 petals here, actually is 22 and a half. It's 45 divided by 2, so 22 and a half. That's why this one is at 22 and a half degrees. And then just remember your petals should be equally spaced. So the only other thing that we talked about, I'm going to kind of zoom out a little bit here for a second, is how do you figure out where all the rest of your petals go? So like, for example, this one, you got your first petal at 30 degrees, but how do you figure out where to put your next ones? Well, out of the entire circle of 360 degrees, if you know you have 3 petals, you divide by 3 and you get 120 degrees in between each petal. And so what that means is there's 120 degrees here, there's 120 degrees here, and there's 120 degrees here. You guys won't use this thought that often because most of the time we do simpler ones where there's like 4 petals, for example. In that case, you just use all the 45-degree reference angles. But in the case of a slightly more challenging one like this one or this one, use those formulas that we have down here to find the first petal location for sine. You do 90 divided by n. Remember, the first petal location for cosine is always at 0, so you don't have to do that for cosine. It's always 0. It's only for sine to figure out where your first one goes. Use this. And then the number of degrees in between the petals is 360, the entire circle divided by number of petals. So it's the same thing here for this cosine one. We knew where our first petal was, but there's 120 degrees here, there's 120 degrees here, and there's 120 degrees there. Okay, only other thing I haven't mentioned yet is how long are these petals supposed to be? Remember, that's right here. That's this first number. This petal is 3 units long, this one's 3 units long all the way down. This is also 3, this one's 4, a little bit longer, and that's where that number comes from. So that's the A value that you're going to be using for your general form. So here are the notes that we wrote down and the sketches that we did in class. I've already talked about all of this stuff and things that you wrote down. Here's the two different location or like formulas that we use in order to figure out petal locations. And then this is what your general form looks like. The N is this N down here, helps you determine how many petals. And remember, the A is the same thing as the circle. It represents the length of the petal. Okay, let's do the Lemniscate. We called it limp biscuit, I think, or Lemniscate. A lot of different ways to pronounce it. So it looks like a figure eight. And hopefully you recognize this word as a figure eight. And it's the only formula that's an R squared. So notice I have that in our general form here. And so in this case, all of them have 2 theta. So you don't have to worry about like how many petals are there or whatever. The R squared formulas always only have 2 theta. So they're just figure eights. And remember, for cosine, it's along the x-axis, and for sine, it's at 45 degrees. And that's always going to be true. The length of your petal is the square root of this number. So just don't forget to square root it. I couldn't draw this as 25. I would run off the graph. Make sure you square root it. It is 5 units out. And you just go at 45 degrees. We talked in class about how you can plug in 0 degrees here and get this point and this point. And you can plug in 45 degrees here and get this point and this point, just to be sure that your graph is located in the right spot. Big note to make for yourself, make sure that you square root the A value if you're coming up with the length of the petal, or the A squared, okay? Next one, the Lemniscate. This one was kind of tricky to come up with the rules and stuff for it. But remember that the first thing we noticed was that if it was a negative cosine, it was going to be on the negative x-axis. That's similar to the rest of the graphs that we've been talking about. This one is a positive cosine, so it is along, the majority of it is along the positive x-axis. This one is a positive sine, so it's on the positive y-axis. So that's the first thing that we talked about. And then we'd used this absolute value stuff. What some of you were able to come up with is just look strictly at this number and this number, 3 and 5. Don't worry about the signs, just use the actual numbers. Remember, the sign, the only thing that the sign helps you with is decide positive x-axis or negative x-axis. In this case, negative cosine is here. So now that we've used that sign, ignore it and just look at the number 3 and 5. When you subtract those two, you get 2. That's what I call my min. And when you add those two numbers, 3 and 5, you get 8, and that's what I call my max. And because this one is a loop, because this number is smaller than this one, that means that what I'm going to do is put a dot on the origin, and I'm going to go my min distance this way, which is 2, and I'm going to go the same exact direction for my max, which is 8, and then I just have to create my little heart shape with a loop in the middle. And so the reason why this one is a loop and not a dimple is because the number 3 is smaller than the number 5. That's what makes it a loop. Okay, so similarly, if I go to this one over here, this one is a dimple because 5 is bigger than 3. Again, ignore these signs. This sign is important because it tells you positive cosine, do your heart over here. Okay, and so now after we use that positive sign, just strictly look at the numbers 5 and 3. And what we've done is we've calculated a min and a max. The min is 2, the max is 8 from using the numbers 5 and 3. So that means that from the origin, or the pole is the correct word to be using here, my min distance is 2. So in this case, don't go this direction because that would make a loop. This one's supposed to have a dimple, so go the other way. So go 2 this way and put a dot. My max distance is 8. And that's supposed to be where the bulk of my heart shape is, my Lemniscate, if you will, and that's because it's positive cosine. And so I have this point on my graph and this point on my graph, and all I need to do now is just connect. Okay? The last one in this section that we talked about was this one, positive sine. So I know it's going this way. And 2 is a smaller number than 3, which is what makes it a loop. So come up with your min and your max. My min is 1, my max is 5. So I'm putting a dot on the origin and I'm going 1 on the inside. That's where I'm going to do my loop. And I'm going 5 in the same direction. And then you just have to make your heart with a little loop in the middle. Okay. And so some things that we wrote down about this. I've already talked about all of these things, but if you missed anything, that's that. Remember the A and the B, we're looking at absolute values. The positive and the negative tells you where to graph your limacone in the positive x, positive y, negative x, negative y, but we take the a and the b values, just strictly the absolute values of them, ignoring the signs, and that tells you max distance from the origin or the pole. And so you have to determine whether it's a dimple or a loop and proceed from there. In this case, I'm on the positive cosine axis, so positive x, which means the bulk of my heart shape is over here. This is a dimple one because 5 is a bigger number than 2. Come up with your min and your max. From the pole, my min goes this way and my max goes this way, so that the bulk of my limacone is on the positive x-axis as it's supposed to be. And then you just make your little heart shape with a little dimple right there. This one is another loop one, and that's because this number is smaller than this one, which means when I do my min and my max, which are 2 and 4, and I make the bulk of my limacone on the negative y-axis, I'm putting a dot at the pole, and my min distance from there is 2, so a dot goes there, and in the same direction I'm putting a dot for my max distance, which is 4. And then make your limacone shape with a little loop-de-loop in the middle. Okay, the cardioid is very, very similar to this one. Remember, the only difference between the cardioid and the limacone is the fact that these numbers are the same. So that's 2, that's 2, that's -3, -3. That means that your min and your max, well, your min is always going to be 0. Okay, so that's why there's no loop and there's no going this direction. It's always a dot on the pole and then another dot at your max distance, and because this is positive cosine, go on the positive x-axis. Because this one is negative sine, go on the negative y-axis. And this distance is 6 because that's my max here. So here's our general form. Here are some things to write down, but that's more simple if you're okay with the limacone. Okay, the very last one is the spiral. So this one's a little bit harder. And so what I recommended doing on this one is making a T-chart, because if all else fails, you can always make a T-chart. So what I did here is I just picked some fairly simple radian measures. You could do these in degrees also. It would be the same exact answer in graph. But I picked some fairly simple radian measures to plug into this formula. And so when I plug in 0 here, that means my radius is 0. And that's why I have a dot here at 0. Okay, the next one, what if I use pi over 4, which is 45 degrees? If you plug that in here, then you get an R value of pi over 2, which is roughly 1.57. So if you go out, and again, I did this radius by 2s, just because I knew I was going to have to get bigger than, I think this is 8 all the way out. So I made each tick mark here worth 2. So this is 2, 4, 6, 8, 10, 12, 14, 16. So scaling by 2s, just keep that in mind. But at 1.57, so 1.5, so not even all the way to 2 here. So somewhere here, I'm going to shift up 45 degrees and put a dot. And it's hard to see because it's kind of small. Let's do the next one. If I plug in pi over 2 here, I just get pi, which is 3.14. So my radius is 3.14. So about halfway between the first tick mark and the second tick mark, since they're scaled by 2s. I'm at about 3.14 and I'm going up to pi over 2, which is 90 degrees. That dot should be right about there. Next one, if I plug in pi, right here I get 2 pi. 2 pi is a radius of 6.28. So go out 2, 4, 6, and a little bit farther, and then go pi units. And there's my dot. And you can see that the spiral, if you connect them, is starting to form. Okay, so again, if I do 3 pi over 2 and I plug that in here, I get just 3 pi, which as a decimal is 9.4. So remember, that's almost 10. So 2, 4, 6, 8, 10. But I'm going to go all the way around to 3 pi over 2, which is right there. This is just a T-chart that you have to graph. Okay? The last one is very similar. I also scaled it by 2s, and it's much bigger because it's 4 theta. But if you do pi over 4 and then plug it in here, you get just 3.14. So 3.14 is 2, not all the way to 4, but go up to 45 degrees right there. If I do pi, for example, I end up plugging in here and I get 4 pi, which is 12.56. So your radius is 2, 4, 6, 8, 10, 12, and a little bit more all the way around to pi. And so your spiral is getting bigger much faster, okay? So that's how to do the spiral. I would recommend doing a T-chart. Hopefully that clears up some of your confusion, or is just a good way to review or refresh before the quiz or the test. Thank you guys for watching. We'll do some more practice in class tomorrow. Have a great night.